Hi, everyone, and welcome back now to episode 18 of the G Register Part 2 in our Apollo Guidance Computer Replica series. So we're making good progress getting through a large portion of the kind of the CPU, the control system. We've gone through all of our special and central registers, the A, the L, the Q, the Z, the Y, the B. We talked about the S register and all of our memory, S register up here. Um, we talked about the kind of fixed bank and erasable bank and the extended fixed bank register so we can address memory. And in the last episode, we talked about the G register. And I mentioned that there's this kind of interesting um, functionality in the G register called editing control. And this provides certain left and right shift operations into the data into the G register. So today we're going to talk about that. So as we talked about in the last episode, there's this kind of special functionality that if octal address either 0020 through 0023 are produced under program control, it will perform these shift or cycle operations within as the G or information is loaded into the G register. So what we have here, and I'll just get myself over out of the way. Um, we've got basically these different functions. So we've got cycle write, which will basically take the contents of the write lines and write them into the G register shifted once to the right. We don't do the bit 15 because again, that's parity bit for memory. And in the case of cycle, we actually, the bit that gets pushed off the end wraps around and gets written into bit 16. We also have the shift right operation, which is basically the same thing as the cycle write, except we don't have this little carryover like the cycle command does. In this case, instead of writing the contents of bit 1 into bit 16, we basically write the contents of bit 16 into both 14 and 16. We have a cycle left, which basically shifts everything to the left, also with that little wraparound. So bit 16 goes into bit 1. There is no shift right command, or I guess operation in this case. And then we have this edup, which basically moves everything kind of 7 bits to the right with no kind of carryover. So it just basically will write zeros into all the subsequent bits. So when I started playing around with this and saying, okay, well, how am I going to build the logic to do this? And I looked at, okay, well, should I use some shift registers? Because there are shift registers within the 7.4 series that I could either shift left or shift right, and you can do the carry around. And so I'd have to have each shift register, I think was um, 8 bits, so I didn't need to use two of them. And I could get it to work fairly well for this scenario, this scenario, and this scenario, but not for this scenario because I'd have to do multiple shifts. And the way the shift registers work is based on clock pulse. So every time there's a clock pulse, it would shift one. So was trying to create some kind of synthetic clock that would run faster than the normal clock. So I could actually shift it 7 times within one regular clock cycle. Um, so again, playing around with a lot of different ways that in the end were getting pretty complicated. And so I decided to step back and say, you know what, maybe there's a much simpler way to do this. Rather than using shift registers, why not actually just implement the logic exactly the way that they've kind of laid out here? It's like, okay, I've got one option where I write, bit 1 loops around, bit 2 goes into 1, bit 3 goes into 2, so on and so forth. In this option, it's kind of the same thing, except we don't have this little wraparound. This one we shift everything the other way, and then again, we write it from these bits into these bits. And so what I decided to do is, again, to make it a lot simpler, and so I've made a few changes since the last time you saw this circuit, is before I had a couple of kind of quad, 2-to-1 selectors, and then there's 4-to-1 selectors. And then I realized okay, I could actually use these 74LS151s, which are 8-to-1 selectors. So in this way, and I mean, each one is only 1 bit. So I actually have to have, you can see 16 of them. So here's the actual uh, G register itself. So each one is 4 bits. So I've got 4 of those to cover the 16 bits of the G register. And then here I've got this kind of matrix of 16 of the 151s. And so I can actually pick the inputs that I'm actually going to load into the G register. So this can be this kind of, L08, or in this case, so I'll actually go to my bit 1. So bit 1, if we're running this um, L2DG uh, instruction, bit 1 I write in micro, and then bit 2 I write in L01, and then bit 3 I write in L02, and so on and so forth. I also have the WG control pulse, which is just to write the contents of the write lines into the register. So I have here bit 1 writes write line 1, bit 2 writes write line 2, write line 3, and so on and so forth. And then I can start actually getting into some of my shift, right? So in this case of my cycle left, or sorry, cycle right or shift right, I can say, okay, well, I now write in the contents of write line 2. And I do that in both of these scenarios. The only time it's different is that wraparound. So that is if I go all the way here and look at my 16-bit, if I'm just doing the shift right, I just write in the contents of 16. Otherwise, I wrap around and do bit 1. Um, and then I can also do, if I'm shifting the other way, I'll write in the contents of write line 16. And if I'm doing the EDOP, I'm just shifting 7 times. So write lines 8 goes into bit 1. So basically, this allows me to kind of do all those shift registers shifting simply by picking what write line input I want to actually load into the appropriate bit for my G register. The other thing I realized I had forgotten when I was looking at when I was designing it kind of last time around is there's also the scenarios that where the G register is our memory buffer, right? So it's also buffering memory that is written to our erasable memory, but it also contains the contents of either our fixed or erasable memory that we're bringing back in. So we actually need to have a scenario for, and I'm just calling these GEM, so that's our G memory kind of bus, in order to bring the data in either from fixed or erasable memory in this scenario. So that kind of covers off 7 different potential scenarios, which allows us we basically use 7 of our um, inputs in our selector to pick the appropriate output and then use that to write into our G register. The 151s also have an inverted output, but we're not going to use that for anything. And then we also have in this case, the 8th. I use the 7th bit basically that we're not using. So in this case, I'm just going to basically pull it low, so it'll always be zeros, but we're never going to select that. So in order for us to pick then, okay, well, which ones do we actually load in here? I need to look at, okay, we basically got these 3 bits, right? So these 3 bits gives us 8 combinations to pick which ones that we want. So basically tie all of those selector lines together. And then what I've done here is basically used a 3 or basically 8-to-3 encoder, so a 74LS148. And so this is basically what by picking or basically pulling low either pin 0, 1, 2, 3, 4, 5, 6, 7, it will generate the appropriate sequence values that I'll need. Now, in this case, I do need to invert them because you can see on the 148, they come out inverted, whereas these are not inverted. So we've got those bits there flipped. And basically, I've got a bit of kind of glue logic here that takes the contents of our S register. So basically what memory address is currently contained in the S register. So I have this one, which basically just checks the high bits in the shift register to ensure that they're zero. Because if they're all zero, then we can basically use 1, 2, 3, and 4 of the contents of the S register to determine, are we doing the CYR, shift right, or sorry, cycle right, shift right, cycle left, or EDOP, and we'll pick the appropriate, basically pull the appropriate pin here low, so it will generate the right value here to select the correct input. And then we also have the options for the WG or L2DG control pulse, which will again pick the appropriate input. Also have one other scenario here where we have basically the read memory. So there's certain timings that we will read the contents from memory. So I'll in a moment, I'll just flip back to the S register and show how we generate that. But basically, based on those timings, we'll generate the appropriate signal here. And because we also have to trigger a write into the G register, I've basically added that as an option. So we basically will write the contents into the register on either the L2DG, the WG, and read mem. And so you may wonder, it's like, well, what about all these like editing control? So these editing controls are actually triggered on a WG command. So if I do WG and S register is set to any of those combinations, like the 020, 021, 022, or 023, it'll do these shift operations. If it's a different address, it'll just straight write the contents of the write lines into the G buffer. So that will solve our problem here. Like I said, the one thing I'll probably be looking at a little bit further when I have to start debugging some of this is looking at some of those control sequences where we look at the actual instruction and how it generates or sub instruction and how it generates the control pulses is, clearly if, the read mem should be at certain time cycles. And I want to just see, do they conflict with the WG signal as well? Because definitely want to make sure that we're writing the contents. Basically, we don't want to have a collision between pulling contents from memory to write into the G register versus the write line commands, or basically when we want to write contents from our write lines into the G buffer. So that's something I'll probably be looking at this week, and we can report back on that in our next episode. The one thing I mentioned is like on the S register, I did add a little additional little circuit here, which is our kind of read mem. And basically we have the two scenarios. So we have this timing. So this is for our erasable memory. So this is our output enable. So that's when we actually push contents. And I'll actually have to update this because these are actually not the G register. This is that G memory register. So that GEM contents here. So we've got that scenario, and that occurs at either T11, T12. And then we also have our scenario up here where we're basically writing out the contents of fixed memory, which occurs at T7. And so, memory or basically contents of either the fixed or erasable memory will be on either T7, T11, or T12. And so that'll generate our kind of read mem control pulse that I'm going to use to determine when we should be writing the contents into our G register. Yeah, so here's basically the bill of materials. I haven't started building my G register. It is going to be on the same board as one of my S registers. So right now it's just a blank board with a label on it. But as I start building it, I'll start putting some pictures together to what it's going to look like, but it'll be kind of the same kind of circuitry. And in order to build this, we'll have 4 74LS173. So this is our 4-bit D registers. Of my 16 74LS151, the 8-bit, or basically 8-line to 1 selectors. We'll have 2 octal transceivers that we do on each of our boards for clock and reset, and then one 74LS148. So this is the 8 to 3 encoder that we're going to use to basically select which of the inputs we want to use for our 151s. And then for glue logic, we've got 2 74LS04s, one 74LS02, 2 74LS10. So these are tri or triple 3-input NAND gates, one 74LS27, triple 3-input NOR gate, one 74LS32 quad input or quad 2-input OR gate, and then we've got buffer. Sorry, actually the octal transceivers are used to read or sort of write the contents of the G register out onto the write lines, and then we've got the buffer here, the 74LS125 that we're going to use for our clock and reset. And of course, because we're storing data in here, we'll have the 16 red LEDs, our bus resistors, decoupling capacitors, and our connector for our bus. So with that, yeah, like I said, it started out looking like the G register was going to be a lot more complex, but once I just kind of said, hey, yeah, I'll just bite the bullet and put 16 of these selectors in, it suddenly became a lot simpler. So for the next episode, I think we're gonna, before we get into our SQ register, which is the sequence register, and that's actually how we basically decode instructions and determine which control pulses we need to be generating based on the actual instruction. I'm going to cover what we call branch control. So the AGC has basically 2 branch bits, BR0, or sorry, BR1 and BR2, or is it maybe BR0, BR1? Anyway, there's 2 bits that determine basically branch instructions. And those are an important input into the sequence register, because we'll have the sequence register, which will say, okay, what is the instruction that or sub-instruction that the computer is running, so we can actually use that to decode control pulses. But the way that also works is depending on the contents of our branch registers, we will execute slightly different control pulses. So we'll kind of look at that in the kind of control pulse sheets, where it shows how the sub instructions decode into control pulses, and we'll see how that kind of conditional logic works. And that's, if you saw the Ben Eater's videos, that ability to do branching is a fundamental aspect of making the AGC a Turing complete computer, so that it can actually run programs. And the way that these branch registers are set is there's a number of sub-instructions that basically perform a variety of different tests. So you can basically evaluate, is the contents of the accumulator 0? Is the contents of the G register 0? Is it a negative number? Is it a positive number? So there's several kind of these like test control pulses that basically evaluate the contents of a variety of different registers, and based on that particular test, it will write certain patterns into those branch registers, and then those branch registers will then be used to determine or generate specific control pulses for basically evaluating whether the instruction should execute one way or execute a different way. But that's what we'll cover in the next episode. As always, if you want to continue to be notified when the next video comes out, please click subscribe, and feedback. Always love feedback. So if you see something I've done wrong, let me know, because I definitely want to fix it here before I start building the hardware. And any suggestions, any comments are always welcome. So we'll expect to see the next video in about a week. And in the meantime, hope everyone has a great week. Thank you.